EDX Decision 1. Algorithms, sorting, packing and other algorithms. The efficiency and order of algorithms. To compare how well algorithms work, we define the following. The efficiency of an algorithm is a measure of the runtime of the algorithm or how long the algorithm takes to produce a result. And in most cases this is proportional to the number of operations that must be carried out. The size of the problem is a measure of its complexity and how difficult it will be to solve. And so in the case of sorting algorithms, for example, it is likely to be the number of elements in the list that determines the size of the problem. The order or the complexity of an algorithm is a measure of its efficiency as a function of the size of the problem. So it's a way of measuring how complex an algorithm will be in a particular scenario. Many algorithms that you come across will be of quadratic or cubic order. So you may see the written as order n squared or order n cubed, where n is the size of a problem. This is helpful. If you know the runtime for a particular value of n, then you can estimate the runtime for larger values of n. Some algorithms are said to have an exponential order. For example, they may be of order n factorial or 2 to the n. These might not be practical for large problems because n factorial and 2 to the n are both exponential growth, and therefore when the problem gets bigger in size, the complexity can become too huge to use in practical terms. The order is usually based on the worst case scenario for an algorithm. So let's keep it simple. For a bubble sort algorithm, we might look at the number of comparisons needed. What would be the worst case scenario for a bubble sort algorithm? Well, the worst case scenario for a bubble sort algorithm is if all the elements are in the reverse order from that required. That is going to be the least efficient way of getting them into the correct order. So for example, how many comparisons are needed to sort the list 5, 4, 3, 2, 1 into ascending order? So you can see that the list is in reverse order, therefore the number of comparisons is going to be, we're going to need 4 for the first pass, then 3, then 2, then 1. We're going to need 10 comparisons to put that list in ascending order. Generalizing this result for a list of size n, the total number of comparisons needed. So in the first pass, you're going to need n minus 1 comparisons. In the second pass, n minus 2 comparisons, etc., etc., until you need 3 comparisons, then 2 comparisons, then 1 comparison. Using the sum formula for the sum of natural numbers, the total number of comparisons is going to be the number of terms in the pattern times the number of terms in the pattern plus 1 over 2. And this simplifies down to n minus 1 times n over 2. So you can see the ideas nice and clearly there. So the total number of comparisons we've seen is n times n minus 1 over 2. This is said to be of quadratic expression or quadratic complexity. To determine the order or the complexity, consider what happens when n is large. When n is large, the dominant term here is n squared. If you expand these brackets, it's n squared is the dominant term as n gets bigger, and therefore we say it's quadratic complexity. So here we have an example. computer takes 0.015 seconds to apply a bubble sort algorithm to 2000 numbers. Estimate the time it would take to apply a bubble sort algorithm to a list of 40,000 numbers. You may assume the algorithm has quadratic order. So, if we look at the size of the original problem, so I'm going to set this out as a little diagram. The size of the original problem was 2,000 items. The size of the new problem is 40,000 items. So what's the multiplication factor? The second problem is 20 times bigger. The second problem is 20 times bigger. Because the bubble sort algorithm is quadratic order, so because this algorithm is a quadratic order, that implies that if the problem we're going to do is 20 times bigger, then the complexity is going to be 20 squared times more complex. So it's 20 squared times more complex than the first problem. So the time for this second problem is going to be the original 0.015 seconds times 20 squared to take into account the complexity. So the approximate time for this new problem would be 6 seconds. You may not have come across Kruskal's algorithm yet, but it does have quadratic order. So the problem is a computer using this algorithm to find the minimum amount of cable needed to connect 150 locations on the map will take about 2 seconds. Calculate approximately how long it will take to apply the algorithm to 2,000 locations. So again, if we look at this as a little diagram, so look at the size of the original problem. The original problem was 150 locations. And if you look at the size of the new problem, that's 2,000 locations. So this new problem, if you divide 2,000 by 150, the multiplying factor is 40 over 3. So it's 40 over 3 times bigger as a problem. Because Kruskal's algorithm has quadratic order, that implies that to do this new problem it's going to be 40 over 3 squared times complexity. It's going to be that times more complex. So in order to work out the time for this new problem, the 150 location problem takes 2 seconds. Therefore this problem we need to multiply by 40 over 3 squared because it's quadratic, so we need to square the size factor, 40 over 3, and that gives us an approximate time of 356 seconds to the nearest second. And that brings us to the end of this section, looking at sorting, packing and other algorithms.